Normally, the motor is operated without any feedback, and that's by using V over F. But once there is feedback, we can change the control method to vector control. Now our system will be known as closed loop. But why we need the feedback and change the control method? The reason is better performance, which will give precision and better handling of torque. In normal method like V over F, there is motor slip. This slip is the difference between the actual speed and the commanded speed. For example, VFD is commanded 1400 rpm, but the actual might be 1325. And this is not constant. If the motor is loaded more, the slip will be greater. With encoder connected, VFD can know the actual speed and compensate the speed difference by increasing or decreasing as required. So we get the precision. This is particularly important in elevators, which will help in getting the correct floor level. Also in textile, where if out of precision, speed can affect on thread quality. The second feature, which is torque, that is the beauty of vector control. Since it can provide full torque at 0 Hz or 0 rpm. And that's the reason using vector control is known as similar to using DC motor. With better torque, applications like hoist or crane will be easily set. So what we require to program vector control? We need to know the motor details and we need to know the encoder details. To connect the encoder, we should check if the encoder card is available in the drive. For some drives, it's built in, but for some we need to install option card. And there are some drives which do not have encoder card option. So we need to plan these things before installation. We have generally three types of encoders: incremental, sinusoidal, and nth. But here we will discuss only incremental. To connect encoder, first check what is the type of incremental encoder. It could be line drive, open collector, or other type. We need to know since this need to be selected in encoder parameters or on the card or both of them. You can see an example of connection on the screen. After connections are done, power on the drive and remember to take caution to never wire when the drive is powered. There is a chance that encoder card can get damaged. Second caution is related to cable of encoder, since any electrical interference can cause problem to performance. So keep the encoder cables far from power and motor cables. And if you need to extend, use shielded cable. For parameters, we need to follow a sequence. First, we need to enter motor parameters, which are motor base frequency, rated kilowatts or horsepower, rated current, rated voltage, motor slip frequency, motor poles, efficiency, and no load current. Plus, we need to enter the supplied frequency and voltage from the source. Then enable encoder to be used as feedback. Set the encoder pulse. Now set the motor as forward or reverse and observe the direction in APO group. In APO number 8. In case forward is commanded and it shows negative, then we need to reverse this in APO number 5. I will demonstrate this in next video. Once done, then perform the auto tuning. If possible, do the rotational tuning, otherwise there is standstill tuning option. Once tuning is done, select the control method to vector control in DRV group, in DRV number 9. Now test run the motor and check if there are any performance issues. If there are torque issues, increase gradually P gain in CON group, CON number 12. And if there are any precision issues, decrease eigentime time in CON number 13. Here I am sharing parameters which I loaded in the drive for demo. In step 1, I took the data of motor and loaded. Second step is encoder setting. So I have enabled encoder as feedback and selected its type and programmed pulse, which in my case is 1024. After encoder enabled, we need to check the direction. I will demonstrate that in next video. Once done with encoder, do the auto tuning. I have chosen standstill type since free shaft was not possible. As shown on the display, tuning is ongoing. It will take a while. Once tuning done, we set the control mode to vector control. I am keeping P gain and I gain as default. Plus I have defined torque limits. The limits can range from 0% to 200%. Here I am showing on the right side of the screen vector control demo and on the left side V over F to give a comparison. We will see torque improvement in this video, which can be observed by the current supplied to the motor for V over F method versus vector control. It shows a big difference whether it is in low speed or high speed. Vector control manages very well. In vector control, we are using motor more efficiently. Now in the second video, we will focus on precision. Just notice the frequency. As soon as motor dips, the VFD gets the feedback and it brings it back to the commanded frequency, which is 15 Hz. This is possible because we have encoder to give feedback. If this was the case with V over F, we couldn't know if the motor is on the commanded speed or no. Before closing vector control topic, I will share my thoughts. In vector control, there are a lot of parameters, but simpler we keep, the better it is. Otherwise, understand very well the parameter you intend to change. And last thing I want to discuss is sensorless vector, which means vector control but without any encoder. This method relies on estimated values, which can be less accurate than sensored vector control. The setup for sensorless vector is almost same like vector control. But do not consider this method in applications like elevator, hoist or cranes, since there is a chance of miscalculation and it can cause disaster.